I'm Russell McClellan. I'm working at SoundWide. I'm a principal software engineer, and my current role is architect of the audio production products. Wanted to shout out my colleague Roth Michaels, who we co-developed this talk together, and he gave a version that went more into the C++ details at CPPCon. So if you get through this talk and you just need more C++ facts, I recommend checking that out. My version is going to be kind of more audio focused. So about SoundWide, if you haven't heard of us, this is a company with kind of a bunch of brands that used to be their own companies. I'm from the isotope side, so the products that I work on and most of the anecdotes from this talk are going to be from isotope products. So the point of this talk is to just sort of go through our journey with learning about undefined behavior and really starting to address it in our organization. So really, I'm trying to take you through understanding what undefined behavior is, all the way to having a practical solution for how to address it in your organization or your company. So yeah, we'll talk about what undefined behavior is in general. We'll have a lot of very frequently asked questions. We'll have a couple of examples of undefined behavior causing weird problems, which is always fun. And then we'll start talking about kind of the concrete steps we took to start addressing it. So for a warm-up exercise, imagine you see this in code review. Somebody's trying to write a white noise generator. What's your response? Missing a semicolon. Yeah. Okay, so now we fixed the semicolon. What's the vibe here? Is this a white noise generator? The answer is we don't know. It's undefined behavior. The compiler is allowed to compile it any way the compiler wants to. And it could be a white noise generator. So we'll talk more about that in a second. By the way, if you want to really understand how to write a white noise generator, Roth, who I mentioned earlier, is giving a talk tomorrow on that. So undefined behavior. In C++, we sort of divide behavior into these kind of four categories. There's defined behavior, which the compiler guarantees how it's going to behave. There's implementation-defined behavior, which the compiler and the operating system have to document, and it has to work the same way every time, but it can be different on different compilers and on different operating systems. There's unspecified behavior, which means something's got to happen, but we won't tell you what, and it can be different each time. But it still has to be kind of a valid version of the program. So the best example of this is function argument order. So if you make a function call and you pass in multiple arguments into the function, you don't know which order those are happening in, but it has to happen in some specific order. So then the last category, and there's this huge gap between unspecified behavior and undefined behavior. In undefined behavior, the standard really doesn't say anything, and compilers can assume this never happens. So if you write undefined behavior as a programmer, the compiler is allowed to compile that however you want. So sort of maybe another way to think about this is if your program has undefined behavior, it's not really a correct C++ program. So when I first heard about this, I kind of thought of it as a sort of horror story. Like, if I don't follow a bunch of arbitrary, arcane rules, the evil compilers will blow up my computer. Or the classic example is making demons come out of your nose. As I've learned more, I kind of have stopped thinking about undefined behavior that way. I rather think of it as a sort of trade between me and the compiler. So the programmer is responsible for writing a correct C++ program, and then the compiler can assume that undefined behavior never happens, and it can use those assumptions to make optimizations. So the compiler optimizations, as I'm sure you know, in C++ are mind-blowing. They can auto-vectorize loops. They can reduce instruction counts by, frankly, science fiction levels. And undefined behavior is sort of part of the engine that makes that work. The fact that the compiler can assume undefined behavior will never happen enables these optimizations. All these images are AI generated too, so that's why they look a little bit off. Can't do any copyright violations. So yeah, I'm going to go over a few examples of undefined behavior. If you're familiar with C++, you've probably seen these. One kind of interesting thing is there's no way to list every behavior that's undefined because it's those behaviors that aren't defined. So sort of infinite amount of those. So initialized variables, which I went over earlier, uninitialized variables rather, if you use a variable and it was never initialized, that could be compiled any possible way. Accessing object after its lifetime is over. So in this example, we're creating this variable x in the middle there. We're then assigning that to a pointer p. Then we're killing x, and x's lifetime is over. And then we're dereferencing the pointer to that. That's undefined behavior because we're accessing x even though its lifetime is over. Out of bounds, so if you have an array of 8 elements and you try to access the 27th one, that's undefined behavior. This is a weird one, the one definition rule, where if you have kind of 2 compilation files that you're going to link together later, and they both define the same function in a different way, often the linker will warn you about it, but sometimes there's flags where the linker can ignore that. And if you do run this, that's undefined behavior, which, again, is kind of strange. You might think it should be unspecified because it surely is going to call one of those. But actually, that's not the case. It could legally call a third version that it just made up. Data races is probably for audio programmers our favorite form of undefined behaviors. This is when 2 threads are accessing the same variable at the same time, and one of those threads at least is going to be trying to modify it. So in this example, we have a value, then we kick off a thread to set that value to 7, then we read it, and then we wait for the thread to finish. So between these 2 lines, there's no kind of concrete ordering about which one happens first, so that's a classic data race. And in audio programming, of course, we often have multiple threads, and this can be pretty scary. I also like to think of breaking the contract between the plugin and the host sort of in the same category as undefined behavior. So each plugin format sort of defines rules on what the plugins are allowed to do, what the hosts are allowed to do. So for example, the Steinberg VST3 SDK has these great diagrams of exactly who's allowed to call what when. And if you break those, it's sort of the same idea as C++ undefined behavior, where the contract is over and the other side is kind of free to do whatever it wants if you make a mistake. Yeah, and then the threading rules, again, get very complicated, especially the interactions between the plugin format threading rules and the C++ data race rules. So if you're a plugin, in many formats, the host can kind of call you on any thread. So you have to make sure no matter which thread the host is calling you on, you don't get a data race. Yeah, the other thing about plugin formats is the contracts can kind of be a little bit hard to read or like hard to understand. C++ is an international standard, so there's like very clear rules that are, it's an international treaty actually. Plugin formats aren't really like that. Usually they're made just by companies and we all sort of agree to them. So it can be complicated and like even frustrating sometimes to determine what the contract even is. All the formats have pretty good docs and are improving them. We're also here at an audio developer conference, and many of the creators of the plugin formats are here. So if you have a question, this is a great time to get them answered. In my experience, these people are really generally very willing to help you understand the details of the formats rules. Obviously, it's in their interest for you to be following the contracts rather than just breaking them. Yes, that's a kind of whirlwind tour of what undefined behavior is, both in C++ and plugin formats. When I first learned about this, I had a lot of questions, and I think if you're trying to kind of like upgrade your organization's understanding of undefined behavior, these questions will come up over and over again, so it's good to have answers to those. So the first question that you often get is, like, won't any problems with undefined behavior only affect that one part of the program that does the undefined behavior? And the answer is no, it could affect any part. And this is sort of the key difference between unspecified behavior, where something's going to happen but you don't know what, and undefined behavior, where your program isn't even a program and the compiler can do whatever it wants. So there's a great example, or a series of examples that I've borrowed from Raymond Chen from Microsoft that really taught me a lot about this issue. So imagine you have a function called value or answer, and it takes a pointer. And then it's going to check to see if the pointer is null. If the pointer is not null, it dereferences the pointer. And if the pointer is null, it returns the answer, 42. Right? So that's actually totally a fine program. But then if you add this one line ahead of that line, you're printing the value of p. You may notice that if p is null, then dereferencing it is going to be undefined behavior, right? But the compiler can know that you're not writing undefined behavior because that's part of the contract, and you definitely are an upstanding programmer who would not write undefined behavior. So what the compiler can do is optimize this program into this, right? It can just get rid of the null check because it knows for sure that p is not null because you just looked at it, right? Does that example make sense? Cool. So more complicated one that's a really cool one. If you haven't seen this before, it's good. So if you have the point of this program is you have a table, which is an array of 4 integers, and someone was trying to write a function that was checking to see if a certain value was in that table, right? So what they did was they did a for loop over the table, then for each value, they said, okay, is that index in the table the value I'm looking for? If so, return true. If not, return false. Does anybody see what the problem is with this? Yeah. So they meant to write a less than, but they wrote less than or equal. And what's really interesting is what the compiler does when it sees this. So to understand the compiler's chain of reasoning here, let's break it into two cases. So one case, the integer is in the list, right? And in that case, it's going to loop through. And before it gets the out of bounds number, it's going to return true, right? And in the other case, when the value isn't in the list, we're going to loop through until it accesses, when I equals 4, that's going to be undefined behavior. But the compiler knew that you didn't write undefined behavior, right? Because you wouldn't do that. So the compiler can compile it into this. And actually, modern compilers do this. This is really, like, if you put it in any optimizing compiler, this is the result you'll get. So you burned the contract, and the compiler's not going to follow its rules either. I think these are really compelling examples because, like just adding a line above it can break it. It's not a local change, this undefined behavior. So then once you understand how bad undefined behavior is, I think the next question is, can't the compiler automatically find everything that's undefined and then give me a compiler error rather than doing something I obviously didn't mean? I was trying to write it, does this exist in the table, and I got it true? The answer is there's actually a mathematical theorem that says this is impossible. It's called Rice's theorem. So any non-trivial property of a program is what's called undecidable. So that means you can't 100% find all the undefined behavior. But this isn't sort of a death sentence that tools can't help at all. So as we get into the tooling section later, we'll see you don't really need to find 100% of the undefined behavior. And also, you can run the program. So there's a couple ways out of this, but there's a theorem saying the general case is impossible. Another thing is okay, and this comes up a lot, why don't they just define all the behavior so there isn't any undefined behavior left, and then I don't have to worry about this? And this is actually a pretty controversial question in the C++ community because it's kind of a place where C++ is out on a limb here. So I looked through the top Stack Overflow languages, and of the top, I think 15, the only 2 that had any behavior that wasn't defined were C++ and C. So this is really a kind of core part of what C++ is. And I think C++ developers, the people who are developing the C++ compilers believe that it's a core way they can get optimizations that other languages can't. It's really a core design principle of C++. And if you don't like undefined behavior, well, you can kind of choose any other programming language because C++ is the most popular one with undefined behavior. For real-time audio, of course, your options are more limited. We saw C major just now, also Rust, but you don't have so many options for real-time audio. So as we always say, C++ gives you enough rope to shoot yourself in the foot. More FAQs. This one I've heard so many times. I tested my code. It has UB. It works. What could possibly go wrong? I even stepped through and read the assembly, and it was all fine. So the answer is it is fine, but it won't be fine if you kind of do anything, right? If you upgrade, maybe the DAW upgrades its version. Maybe you've changed the optimization settings. Maybe you have a different compiler, or any of these things. Also, it doesn't even have to be this dramatic. Sometimes optimizations kick in and out if you just move code around. If kind of 2 functions that used to be in different files are in one file, the optimizer might optimize it differently. So there's a lot of ways where you can be in a safe space for now, but you just do one thing, and now your program's broken because you had the undefined behavior in there. This is a great quote from Titus Winters from Google. Software engineering is programming over time. Yep. This is a kind of maybe a kind of subtle, pretty much the same thing as the previous question, but coming from a slightly different perspective. So if you think you know what hardware instructions my code will compile to, and then I read the manual, the Intel manual, which says these instructions will totally work, so my undefined behavior is fine, right? And even in this case, C++ doesn't guarantee, and no compilers that I know of guarantee which hardware instructions a given C++ program will turn into. So even this isn't enough confidence to leave undefined behavior in your code base. It's really not fine. And it's kind of an example of this that we used to have in our code base. We had this function called atomic read, which is supposed to be our thread-safe read. And you can see its implementation was just return X. And then there's this long comment about how it's fine because I'm totally sure I know which Intel instruction this return X will compile to, and it's guaranteed to be atomic, even on multiprocessor systems. So even though they use fancy words, this chain of reasoning just doesn't hold because it makes two assumptions, right? Like it makes the assumption that you know what the C++ compiler is going to do, which you don't with an optimizing compiler. And then also it assumes we're running on Intel, which these days isn't a good assumption at all. Like this computer is not an Intel computer, and we want our code to be portable. We might be running on the web, for example. Yeah, and then finally, there's just sort of like the ad hominem attack. Like, isn't this just an esoteric academic concern for people who love C++? Wouldn't really cause problems in the real world. And to be honest, this was my perspective for a long time. And I didn't really change my mind until I saw it cause real problems. So I'll show you some of these that we ran into. But also, it's something to keep your eye out on your own. And the other reason is that if you break plugin contracts, people will call you names. We had, in 2017, someone once said, those guys are not serious programmers. And we've carried this with us as a burden since then. And words can hurt, but they can also inspire you to do better. So for this, I thank someone on some internet forum. So yeah, now I'm going to talk about a couple of concrete instances where undefined behavior gave us grief. So the first case study is attack of the Xcode update, C++ undefined behavior, causing weird stuff. So this was back during the development of one of the versions of RX. This is a program we make that is like an audio repair tool, so you can do all sorts of repairing and editing of your audio in this tool. So this was like kind of an upgrade. We already had a basic system, but we wanted to refresh the UI. So one of our UI designers, who was really good, was building the code locally so they could kind of make changes to the code, change colors and stuff, and then recompile it and see the results. However, they installed Xcode with the Apple App Store, which auto upgrades. So after one upgrade, the program, which was supposed to look like this, looked like this. So it's sort of a subtle difference. I'm not sure if you can see it. But yeah, basically in this dialog, that's supposed to be a circle, but it's actually that weird kind of ovular shape, right? So just that's what it's supposed to look like. That's what it looks like. And that's not right. So my first thought, Roth and I both thought, this is probably a compiler bug, right? Like it was working in the old version, not working in the new version. Yeah, it's got to be Apple's fault. So my first step was to jump on the Clang IRC and be like, hey, you've got a bug. You're compiling circles into weird ovular shapes. And they didn't really respond well to that, I don't think. Yeah, because I was wrong, right? But so then our next step was, Roth and I, like I had the old version, Roth had the new version. We were kind of like shouting x86 assembly instructions to each other, like move RSP RAX, and then we were trying to. So eventually we found the place where it compiled it differently, and yeah. So spoiler alert, we didn't find a compiler bug. Probably. Usually when you think you find a compiler bug, you've found undefined behavior in your code base most of the time. So kind of to dig into exactly what was going on here. So this was kind of the function, or kind of a skeleton version of the function that drew the circle. So we're making this ellipse object. Then we're kind of applying a transform. So in this case, it was like for retina, right? So it might be might have to scale it up, or it might have to not scale it up. So we're applying a transform to the ellipse, and then we're adding that to our rasterizer. And this actually, it's not obvious what the problem is yet until you look at the constructor for transform. Right, so this takes two arguments, both of them as references, and then it converts those references into pointers and then store those. So when we go back to this function, you can see that when we add the path to the rasterizer, P is going to be dereferencing those pointers. But one of those pointers is going to point to the return value of get transform, whose lifetime is already over, right? Because by the time we get to that line, get transform is gone. But now we still have a pointer to it, and we're adding the path there. So yeah, so that was the issue, that we were just accessing a value after its lifetime was over. And it's kind of hard to imagine how that could turn a circle into this weird ovular shape. But the fact is, like, we don't have a compiler crystal ball. There's no way to know exactly what the compiler is doing. If you break the contract kind of in any way, the compiler can do anything. And for us, this was really a sort of like a moment where we shift our perspective, because it's not just the program can crash, it's not just you can get a weird mathematical result, it's like a circle can turn into, I don't know even what the name of that shape is. The other thing to mention about this is that that code was in the code base for a long time, and we had gone through probably at least dozens of Xcode upgrades without ever seeing a problem. And then one Xcode upgrade was the straw that broke the back, and it kind of broke the program. So the fix, if you're interested, is just to pull that transform into its own variable, so its lifetime lasts the whole function, and then that works. Yeah. So the next case study is about plugin format undefined behavior rather than C++ undefined behavior. And this is one of the most exciting bugs I've ever worked on. I call it the case of the phantom hum. So it all started during the development of Neutron 1, which is our mixing product. I think this is in 2016 or so. I got an email from the PM alerting us to an odd bug. It said, "Hi team, this seems like a particularly odd one. Thoughts?" Yeah, that's a scary email to get from a PM. And then attached was a bug description from a beta tester. It says, "After playing a few seconds of audio, I start to get a hum around 188 hertz. Doesn't matter if the transport is stopped or moving. It starts low and increases in volume. Even if you make a new session where Neutron has never been inserted, the hum persists." So I gotta be honest, when I see beta reports like this, I usually don't believe them. I believe that the beta tester was confused, because that couldn't be, right? In this case, that was completely correct. So I reproduced myself, right? I put a new Neutron in this particular host where the problem was. And indeed, after a minute or two, there was a hum, and it was exactly 187.5 hertz. And it would start off really low, like in the screenshot, it's negative 110, but it would slowly grow louder until it was audible, and it would never stop until you took Neutron off the track. That would make it stop growing, but that would not make it stop playing. So it would continue to play even after I deleted Neutron from the track, right? So this is very weird. Plugins usually are sent audio, and then they modify it and send it back to the host, and then that's what's played. Plugins are not supposed to sort of like ghostly create hums out of nowhere. Yeah, and then even weirder, indeed, you could close that project, open a new project that had never had Neutron inserted, and then the hum would still remain. So yeah, this was honestly kind of a stumper. The one hint I had was the frequency of the hum. So we were running at a 48,000 samples per second sample rate with a buffer size of 256 samples per buffer. And if you divide those out, you get 187.5 hertz, which was the exact frequency of the hum. So that was the hint that it was something kind of buffer rate related. So yeah, after digging in more, we tracked this down to the plugin sidechain. So the sidechain is, if you're not familiar, something that you can kind of send from another track into your plugin, and then the plugin can sort of react to the audio on the other track and sort of combine the two tracks in that way. So it turned out each buffer, we were subtly, minutely changing the sidechain input buffer. So when the sidechain is not attached in this particular host, the host would always pass in a silent buffer as the sidechain input. But it turns out this host had one global silence buffer that it would use whenever it wanted to play silence. So by changing it, we were changing how silence itself sounded. So then it would use the silence buffer whenever the transport was stopped or whenever there was a gap in audio, it would just kind of play back from this buffer that we had modified. Yeah, I was this is a fascinating bug. And I think one detail is that the silence wasn't exactly zeros. It wasn't exactly digital black. If you zoom in a lot, there was this tiny amount of noise, and that was sort of key to why we were changing it on the sidechain input. So yeah, basically what we were doing is we were breaking the buffer into 3 bands, and then we were running analysis on each of these 3 bands, which didn't change the audio, and then we recombined them. But the filters that we're using kind of created this minute difference when you did that operation of splitting them and then recombining them. So this would sort of build up as more and more buffers pass through these filters until we kind of had like little spikes in the noise, and like that's what you would be hearing in the hum. So yeah. So basically always read the plugin spec and never write data to an input, because you're not allowed to do that as a plugin. You might change the meaning of silence. And if you're interested in what the fix was for this particular issue, we just had to copy the input before running it through our filters, and then everything was fine. Yeah. So examples like that kind of made us really understand that like you shouldn't be writing undefined behavior. You shouldn't be breaking plugin contracts. So that was sort of how we changed our mind about this. But there's still a long way from there to like doing anything about it. So we have a lot of code, right? In Isotope, we kind of have 2 million lines of code that we maintain, and then that's not including third-party libraries, which in some ways we're responsible for. And then once you realize how bad undefined behavior is, it can be really like kind of disheartening and scary to even approach it at all. So our strategy, which I think worked really well, is to realize that we were in a hole and we had to stop digging. So the first step was just to prevent ourselves from adding new undefined behavior to our code base. And once you do that, you're in a really good position, because you can start to kind of attack the backlog of undefined behavior that you have with the confidence that you won't backslide. You're not going to be adding new undefined behavior as you go. So yeah, by stopping, you can really be sure the problem will never get worse than it already is. And that's a really good place to be, and stopping is sort of like an achievable goal, I think. Then once you do stop, you do have to kind of look for opportunities where it makes sense to kind of attack undefined behavior that you already have. So by making sense, I mean like actually making business sense, like it being more valuable to do than the time it takes, right? So maybe you have a really bad area that's like always causing problems, or you're planning to upgrade your compilers, or somebody releases a new chip that you have to support. These are strong reasons why you should really attack existing undefined behavior. So yeah, once you decide to do it and you kind of have the basic plan, we're going to stop adding new behavior, and then we're going to address our old undefined behavior. How do you actually do it? So you kind of, in an organization really of any size greater than 1 person, it's a sort of, it's a mix of tools and hearts and minds. So you kind of need to attack the culture, and you need to add tooling improvements. And these really have to reinforce each other, because if people care a lot and they don't have any tools to address any of this stuff, they're just going to be disheartened and scared. But also, if you have the best tools in the world and no one cares, no one's going to use them. So you need to kind of address both of these at the same time. Yeah, so culture changes is kind of the first area I'm going to talk about. But as I said, you kind of can't sequence it to do one and the other. You have to be doing both in parallel. So one piece is just education. So like Roth gave a great tech talk reviewing many of these kind of anecdotes that we had internally when developing one product. And that went a long way to making it feel real to stakeholders kind of across the company, inside and outside of engineering. So undefined behavior is actually like a kind of a real problem, and there's ways to express it that makes sense to kind of everyone in your company. So it's going to be scary kind of in different ways to different stakeholders, right? Like if you're talking to an engineering manager, you might want to emphasize, hey, this is preventing us from adopting new platforms. This is preventing us from being on the latest compiler that's going to give us the greatest optimizations. If you're talking to like somebody in quality assurance, you might say like, this makes testing really scary because any change could cause any bug. Circle could turn into any shape, Yeah, so another thing we did was we actually like wrote a rule in our style guide that you don't write undefined behavior. This seems like a really simple thing, but this was kind of a turning point for us, because I guess it started, we had kind of a debate on a PR where somebody had like called out like, hey, this is undefined behavior, you can't write that. And the response was like, can't I? And that kind of triggered a big discussion in our engineering organization. And kind of the result of that was like, hey, we all agree, like, let's not do this. And then once that got written down, that was something where people refer to that in code reviews, right? People are like, hey, like this is undefined behavior, and we don't do that because we're serious programmers. Yeah, so that was really a surprising like kind of turning point in the culture. Yeah, another big one is we have automation that like test automation that runs on every build, and for a long time, if something went red, we just redo it, see if it does better next time, and if it's green, you sort of move on and you don't worry about it. And one of the things we realize is that can be, if something's failing sometimes but not failing other times, that can be a really big hint that you've actually have undefined behavior somewhere that you need to find. So now that's something that when this happens, we really don't just rerun it. We actually try to see if, is this undefined behavior? And if so, can we fix it? Another kind of related thing is bug prioritization. So if a bug really seems like it's undefined behavior, even if it's not causing a huge user problem, it's something you might want to look at because, again, all the reasons I talked about earlier why you don't want undefined behavior in a code base. So in this example, this is one of our analytics that got sent. So yeah, it's most of these fields look fine, but the primary classifier is 8 and then 3 unrenderable characters. So good guess, something bad's going to happen there, right? Maybe it's reading off the end of a buffer, maybe it's kind of reading uninitialized memory, something like that. So even if this isn't causing a huge problem for the organization, it might be something you want to look at. Yeah. So for tooling, this is kind of going to be. First, I'm going to talk kind of generally my philosophy about tooling changes and then kind of the specific tools that we use. So yeah, it's very important to, the point of tools is to reduce drudgery. And it's really important when you're kind of rolling out tools that they don't feel like work to the engineers who are adopting them, right? Because that's going to be very counterproductive. So you kind of can't have a situation where you fix all the undefined behavior first and then the tools help you, right? So you have to write automated tools that only fail when new code breaks a rule. So that's again, this kind of stop digging philosophy. So if you have a tool like this that only breaks when new code does something wrong, then you can roll it out immediately. You're getting a ton of value because you're not introducing new problems. And then anytime you fix a problem, this sort of acts as like a ratchet to make sure you don't backslide to reintroduce a problem. So really kind of the gold standard for tools, especially for tools finding undefined behavior, is only break on new code, I think. Another thing is, this is kind of my suggestion for how to go about adopting new tools. There's kind of this impulse when you find something really cool to sort of roll it out to everything automatically, like immediately. But that can be really dangerous because you could roll out the wrong thing. And that can be really counterproductive, right? It can make everyone lose faith in the whole concept of automation. So yeah, my recommendation is start with awareness and then get some value out of manually using it, right? Like spot check issues, run it when you think there's a problem, and get value that way. Then sort of choose one project to be your pilot automation. Then only then, when you really feel like, oh, I'm getting a ton of value out of this tool, do you roll it out to kind of every project. It can be really tempting to skip these steps, but I think it's important to not. For an example of how long this can take, while preparing this talk, I found one bug in our bug tracker that says research address sanitizer, which is one of the tools that I'm about to talk about. And yeah, it's been open for 6.8 years. So yeah, it can be a long process, but I actually think that's healthy because you only want to integrate the tools into your automation that makes sense. Another thing to think about is kind of where do these tools best fit in in your pipeline. So there's this concept of the testing pyramid where most of your tests are unit tests that test really small pieces of code. Then you have some integration tests which test pieces coming together. And then you have a kind of small number of end-to-end tests that are really kind of beginning to end test your products. So different tools kind of have a natural fit in different places in this cycle. And it's really important to be mindful and not try to force a tool where it doesn't belong, because then, again, you want to make these things feel like they're helping you, because that's the whole point of them. Yeah, so I wanted to go into some really nitty-gritty, nerdy details on the tools that we use and tips and tricks that maybe might be inspiring to you. So yeah, I'm not going to try to talk about every tool that finds undefined behavior. There's a lot of them. I'm just going to talk about the ones that we have experience with and kind of some of their specialities. Yeah, so compiler warnings is a really big one. So yeah, I'm sure these are not very surprising, but there's actually a lot of good stuff in the compilers. And they keep adding them every version. So yeah, you should definitely aim to have most warnings on. I think we have like all warnings on as errors, and then we turn off a couple that we don't want. Yeah, deprecation warnings, which I'm going to talk about a little bit more, make it really easy to migrate away from bad areas of your code base that are going to be kind of undefined behavior traps. Yeah, and again, kind of you really want to only make the builds fail only when new code creates these warnings. So, that's can be a little bit hard to achieve. Like one way to do it is kind of parsing the log and looking at where those warnings happened and then correlating it to the diff. And in a couple slides, I'll maybe talk a little bit more about how we do it. Yeah, so for deprecation warnings, this is a pattern that we use a lot when we find an area of the code base that just kind of isn't working well. So for example, we had this register parameter call that would always make a data race when you called it. And the problem was like our whole code base used this, so we couldn't just delete it. So what we made is another version that's register parameter, and you can see it takes an atomic T, so that makes it not a data race. And then we added this deprecated attribute to the old version that causes undefined behavior. So once we do that, any code that calls that will have a compiler warning that says you've used a deprecated function. And so this, just by adding that deprecation attribute, we made it so that it'll fail to build if any new code adds that. So that way we can make sure all right, we're never going to use this again in new code, and then we can take our time to get rid of existing calls to this function. Yeah, so after compiler warnings, I would say this is really the MVP of the undefined behavior toolbox, is a tool called clang tidy. So this is distributed with Clang, which is a compiler. It's a static analysis tool for finding C++ bugs, and it has tons of different checks in there for uninitialized variables or kind of different use after free errors or using when the lifetime's gone errors or use after move. It has a lot of these different things built in. The one thing I don't like about it is everybody gets the name confused with Clang format, which is the auto formatting tool. They're unrelated tools. Yeah, so I wish it had a better name. Yeah. So also built in with clang tidy, there's sort of this hidden gem called clang tidy diff. So this is a Python script that's distributed with clang tidy, which is distributed with Clang. And what this does is it automatically will check a git diff and only warn you on errors that were introduced by that git diff. So this is sort of the engine that really drives that sort of stop digging philosophy I was talking about. So what we do for warnings is rather than parsing the logs, we actually enable those warnings only in clang tidy and then have clang tidy work in the clang tidy diff mode so that you can use this clang tidy diff check and then fail builds only when new code introduces deprecated stuff. So yeah, that's really cool. Clang tidy is, yeah, it's definitely the gift that keeps on giving from Clang. So you can write your own clang tidy checks that are specific to your code base. So if there's kind of one class that you really don't want people to use in a specific way, you can write your own check. I've linked to a blog that kind of explains how to do this. The only sort of caveat is the way you add these checks is by recompiling clang tidy. So it does mean that you have to kind of have your own clang tidy version if you want to write your own checks. And that's not all. It can also fix issues for you. So the checks can include ways to modify the code to get around the issues. And this can be for your custom ones or for a lot of the built-in ones. So that's kind of great for large-scale migrations that you want to automate. In addition to clang tidy, we use these things called the sanitizers, which are also sort of distributed with Clang. So there's an address sanitizer and the undefined behavior sanitizer. And you can run both of them at the same time, which we always do. So I don't even know what the difference is between them. But these, rather than clang tidy, which works as a static analyzer that just looks at your code, this runs your code to check for undefined behavior. So yeah, these are pretty nice. You do have to build it specially to run it. And yeah, the other kind of caveat is that you can't, there's no way that I've found to only fail on new failures. So you have to use this in a place where you've already exterminated all of your undefined behavior. And this can be a very great way to make sure you don't add even the undefined behavior that clang tidy can't find. Thread sanitizer is another one of these kind of tools. So this one focuses on data races, which the other tools don't really focus on. For us, this is kind of still in that manually run mode because we haven't found a way to make it as foolproof enough to automate it. But we've still found and fixed a lot of data races we never would have found without it. Yeah, there's a couple of kind of details. Like there's this one atomic thing that's called atomic thread fence, which is part of the standard that thread sanitizer just doesn't know about. So if you're using it, it says you made a mistake even when you didn't. Yeah, for plugin formats, there's a lot of tools there to make sure you're not breaking any of the plugin format rules either. So each plugin manufacturer or plugin format designer kind of ships their own validators for you. Definitely recommend running these in CI with like max settings. So they don't really catch a lot of stuff, unfortunately. They really just focus on the basics. There's a tool called Plugin Val, which was made by Traction. And that's open source, which is really great because if you find it like says, hey, you failed this test, and you're like, I don't know what that test even means, you can just read the code. Another thing for plugin formats that we use internally, and we haven't open sourced this yet, but we're sort of considering it, we have a Python binding to the VST3 format. So we can write Python code that does individual VST3 calls. So if you find like some certain call pattern that some host is doing, and that's kind of making your plugin react badly, you can kind of write a Python script to kind of go through those calls. And yeah, you can kind of basically write your own validation tests in Python. It's also useful just for general automation too. So if you're more interested in that, you can talk to me after the talk. Yeah, so just to conclude, undefined behavior is definitely a challenging kind of area to even understand, and then even more than understanding, it's challenging to fix. So you really have to start making your organization care about it, and then you also have to invest in usable tools that make that care able to be translated into action. Yeah, so thank you. And any questions?